Hey everybody, I hope you're doing well. Um, we've implemented functions. Let me first start with the project was called A, which is a terrible name because it's really confusing, and so I've replaced it with ELO, which is also a terrible name but a lot less confusing, and it nicely fits in as a extension, stuff like that. It means tool in a language called Tokepono. But so functions. This is yeah a great addition to the language because this means that we can make actual programs like Fibonacci. We can calculate the Fibonacci sequence. So this is what it looks like. It's statically typed. So you have to define the arguments here and what it returns, what type it returns. I've also added a main entry point. So this way you can have arguments, which is also a very nice addition. So I made a video about implementing it, but it took way too long to be interesting. So I'm just gonna show you how it works. So let's take another example. This one. So what we have here, this will not compile because we need dev main with the pointer argv and int argc and returns an integer. Yeah. All right. So how does this work? I'll compile this example and we'll just scroll through it. First of all, the start entry point is moved to the end and main is called. In main, let's see. So we push 1, 2, and 3. I'll explain this later on, but let's start here. We push 1, 2, and 3. And when we call add, this is where the label is. So this is where the function is. But before it jumps into add, let's build the stack as it is. That's kind of annoying. So 1, 2, 3, this is the stack. Then we call add, and before we jump into add, we need to keep track of where this call happens in the code. So the address to this call is pushed onto the stack. Well, let's call it IP, which is an instruction pointer. So the value of the instruction pointer is pushed onto the address. This happens within this call, and then you jump into the function. And when the function returns, it uses this value to jump to. So that's how it knows where to get back. Okay, so we jump into add. And what happens next is that the frame pointer, the old frame pointer, is pushed onto the stack. A frame pointer is used to keep track of where arguments are. So, and we use the RBP register to keep the frame pointer. So when we go into a new function, we have a new frame. So we save the old frame pointer onto the stack, on the stack. So, and then we move the stack pointer, which points to this, to the frame pointer register. So the new frame pointer is actually at this location. So let's add that frame pointer. All right. So then we're in the function. We push 1, 2, 3 onto the stack. I'll show you why it's relevant. And then we want to push X onto the stack. And this is where the frame pointer comes in handy, because we use the frame pointer as a reference, and we know that this is x and this is y, and no matter where the stack pointer is, we could be anywhere here, we know that x, for example, is 1, 2, 3, 3 bytes away from, well, 3 units away from the frame pointer. So you just add that offset, and the same goes for y. So that's what you see here. You move the frame pointer to RAX, you add the offset, which is 3 times 8, because it's 8 bytes per stack unit. And then you dereference it. You take the value of which the pointer in RAX points to, which is 2 in this case. You move it to RBX and you push it. And you do the same for Y. And then, so then we have 2 and 3 onto the stack. We add them, which removes the top 2 and puts 5 on there. And then we return. And what we do when we return, we say RAX contains the return value, because we're gonna remove this part of the stack. So we cannot return values over the stack. We need to use registers. So we've designated RAX for that. All right, so 5 is popped into RAX. Then the stack pointer is pointing at the value before that. But we want to, no matter how many values are on the stack, we just want to go to alt frame pointer. So where the frame pointer is pointing at. So that's what we do then. We move the frame pointer, the value of the frame pointer, into the stack pointer. So we don't really delete the values in the frame, but we just ignore them. We act like it doesn't exist anymore. So the stack pointer is looking at that, and then we can pop the old frame pointer back into RBP. So RBP contains the old frame pointer, and then the return opcode is called, which means it takes the IP address and jumps back to where the call was made. So that is here. Well, then we've arrived here, and then we add the values. So 1 and 5 should be on the stack. After the add, 1 and 5 is 6, and 6 is returned. And so if we try to compile this, so test.asm and compile it. We test it, we should get 6, and we get 6. So yeah, that's really cool. What we also could do is like use the arguments, because that's the convenient thing about this way of calling functions. It's sort of compatible with how C handles function calling. We don't have to do anything fancy because to implement arguments, because they're already pushed onto the stack. So what we can do, we can just simply return argc, and then if we compile this, argc is the number of arguments. So this should be 1. Sorry, 1, because it also counts this part. And if we add an argument, we get 2. So that's really cool. We can fetch the arguments and do things accordingly. So that's another way for input and output. Yeah, so that's really cool. So next time, I think I will start implementing a standard library with some string-related functions. And after that, I think the next video will be about memory allocation. So I will create a malloc and a free method. That will be cool. All right. Thanks for watching, and see you next time.